The thought of doing 3 weeks worth of, small math algorithms, I'm not sure would have made anybody particularly happy. So we're going to kind of push through those, and then the rest of the course we're really going to see, two things. One is talk about a lot of programming ideas and kind of abstract concepts which are good for programming, and teach you how to actually build real things that are, outside of really what would be considered the object-oriented programming idea. But then we're going to see how they're implemented in an object-oriented environment like Java, and we're going to use Java to of course, program with them. Somebody printed out this great article by Simon Garfinkel, I think his name is, on, is Java over or whatever. And I read that this morning. That was great. And I think a lot of what he says, toned down a little bit, is probably true. That certainly the write once, run everywhere promise has not really come to fruition as much as it could, nor is it necessarily what people, is it that important to some people. And certainly all the flaming about speed is certainly an issue. You seem to have a certain amount of variance in the amount of memory you have on your machines, because sometimes typing Java X on a very simple program will, it takes a while for that thing to kick in. Whereas if you had the same program compiled in C, it would be over before you could blink. So, on the other hand, all of the principles and ideas we're teaching you in this course, and indeed a lot of the syntax, are directly transferable to a C, C++, fully compiled, fast as hell environment. So the fact that we're using Java to explain this, I see the main benefit of that is that Java is a relatively good and safe environment to learn this sort of thing in. It doesn't have all the sharp edges that C++ does to cut yourself on, and it doesn't have all of the arcane features that you can get lost in that C++ does. But I like that article. Whoever printed it out, thank you.
So what's the conclusion of the article then?
Huh?
So what's the conclusion?
There wasn't any conclusion except that this guy was sick of and hated Java. I mean, to a certain extent, it was just a flame about, he got these programs, they ran too slow, and, he's sick of programming in it, and blah, blah, blah. And, it didn't live up to its hype. I think that was really the gist of it, getting something off of his chest. But there's some truth there. And in fact, that is a good segue into today's lecture. Today we're going to talk about object-oriented programming and the design process. And we're going to look at some of the ideas I talked about last week from a different point of view, and why the people who believe that object-oriented programming is the greatest thing since sliced butter believe that. And then in the second half of the course, we are going to go through a design example. One of the things that is an important skill for programming, but doesn't really come under the heading of anything, is just how to look at a fairly big problem and do a design for it so that it seems doable. So what we're going to try and do is write Tetris in the last 40 minutes of the course, of the lecture. I think to step way back and get the global view, if you think of the two classes of people who are interested and concerned with software, there are your users, who are either the people who go out and buy off-the-shelf stuff or download utilities over the web to use on their machines or in their systems, or they are internal business customers who say, come to some project manager and say, we need to hook this legacy database with this website with this, and get your team to go and write me some middleware. And the end users are the people who have to use that system. And then there's what I would call the producers, who are your poor software project managers, who I'm going to call your PMs, and I'll give them a capital D, since that's us, the developers, who are the people who have to actually design and implement the code. And both of these groups have kind of different concerns in what they want from language and from software. Okay? The user wants something that is efficient, right? When you get a program, you don't get something off the shelf or buy something. You don't care what language it's written in. You don't care what techniques we use to design it. You don't care how neatly it's structured inside. What you want it to be is fast as hell. And even if it's something that's just sitting there waiting for you to type, you know, if it's an interactive program and most of the time it's doing nothing, you don't want, as soon as you type, it to take up all your CPU because, you know, your MPEG-3 player is running in the background and you don't want to interrupt your music experience. So speed does matter. You also don't want it to be this huge program and take up a lot of memory so that your MP3 player won't be compatible with it. So users want something that's fast, that's efficient. They want something that's reliable, that runs without bugs, and that they don't have to do any work for. And they want something that's feature complete, that does everything they want it to do. And they want something that's available and cheap. I mean, they don't want something that you announce in 1999 that doesn't actually become available until 2002. So that's what the user wants. And to be perfectly honest, object-oriented programming addresses almost none of those concerns. It helps maybe with reliability, you could argue, and it helps maybe with schedule and price. Now, what the project managers and developers, you know, they're interested. Let me even write some stuff out. Programmer efficiency, as opposed to program efficiency. I should make my lectures without so many big words. No, that doesn't belong there. Sorry. Right. Thank you. It's the cold. Which means that the project manager has some collection of developers, and his main concern is to get the project done on schedule, or if it can't be done on schedule, at least before it's canceled. I mean, the ugly truth is that 50% or more of all software, industry-wide, of all software projects are canceled before they're completed. All right? And so this is due to maybe lots of reasons. The people who decided to fund it decided it was a bad idea, or it ran out of money, or the developers just built this big monstrosity of code that eventually collapses on itself and nobody can maintain it. Could be all the developers quit to go work for some high-paying .com. It could be that the high-paying.com that was funding the project goes bust. So, I have friends whose projects have been canceled due to all of those reasons. So programmer efficiency. Maintainability. If you're a developer or a project manager and you're developing this, you have this big code base, you need to be able to fix bugs, because no matter how much you test it, as soon as you put it out in the field and let people use it, they're going to find a whole mess of bugs that you didn't envision and feed those back to you, and you're going to have to fix them to make your customers happy. I mean, you can see that just with our little problem set. I mean, I do it and look it over until I can't find any bugs, then give it to the TA to do until they can't find any bugs. But then when you give it out to 30 people, you always find more bugs. The wider your audience you distribute something to, the more bugs that you tend to find. So you need to be able to fix bugs. And often you need to be able to fix them without attention from the original developer team, because they've moved on or quit or whatever. So along with that comes extensibility. okay? You want something that, new features can be added, that can be improved, because programs often don't stay steady, or the market doesn't stay steady. Your competitors aren't staying still. So if you have something that doesn't change, your competitors or some new startup will eventually wipe you out with something that starts from scratch. Finally, the program manager and the developers do have to worry about that the user concerns are reasonably met, because otherwise the user will just go off to their competition and buy their competition's thing, and everybody will be out of a job. So, in truth, it is these issues, more than the user's issues, that object-oriented programming and things like Java were, I think, meant to address, or originally designed to address. And the feeling was that then if they just make it run fast enough, all of the user's concerns will be met. If you read that article by Simon Garfinkel, you can see that that isn't necessarily the case. That something that addresses this group of participants' problems isn't necessarily guaranteed to solve this group's problems. I guess the other point of that article was that Java and object-oriented programming will not turn bad programmers into good programmers. And I believe that is true. If you are a good programmer, then you will write good programs in C or LaTeX or Java. And if you're a bad programmer, you will probably write worse, slower programs as the results of a test in Java than you would even in C. That's the high-level goals that we're trying to accomplish here. And there's some ideas, and over the years, people have written programs and have some ideas about what works and what doesn't. And some principles have emerged that are good. Okay, one of them is I will call encapsulation. This also goes under the term of maybe isolation. There are, some people will give slightly different names to these, but to me, this is basically hiding implementation from interface. Okay. So that's one aspect of it. And another aspect of it is, a consequence of that is that aspects and data involved in the implementation are limited to the routines implementing a certain functionality and are not seen by all of the people using that functionality. Okay? This is a powerful thing, and it goes to certainly reliability, because the fewer people who are touching, the more limited the access to certain variables are, and the more high level you can chop up something, the more reliable it's going to be. Also, the easier it is going to be to change something, because if you can limit the number of people the number of routines, I tend to anthropomorphize programs, the number of routines that can access a certain piece of data, then if you have to change the representation of that data, you've limited the number of places you have to change. On the other hand, if it's wide open, if anybody could have used that piece of data or accessed that variable and you change it, you have to run through every line of code. You have a whole Y2K issue that you've built in. In some sense, the whole Y2K problem was a failure of encapsulation. Our three weapons is abstraction, which has a number of different guises. data abstraction, which is a whole field in itself, which is in part thinking of pieces of things in terms of abstract types like we're doing with classes. So we're working with the idea of a polynomial rather than trying to carry around underlying data structures like integer arrays that we're going to at some points think about as polynomials and sometimes not. So being able to extend the type system so you can make new types that you can think about at a high level and apply and add natural operations to them, like we're doing with methods. This is one aspect of data abstraction. The second is you can arrange these things into hierarchies so you can concentrate implementations on superclasses rather than subclasses. And that's some of the other power you can get out of this. You can factor out common code. And you can factor that out into routine methods on parent classes. All the things that are common among child classes you can implement on the parent classes, and you only have to implement once. There's also a much older and not really object-oriented approach, which is just to factor common code. If you find something that you end up doing a lot in lots of places, just factor that out into a separate subroutine that implements it. And in Java, that would be implemented as a method, of course, but I'll use a more general word. And finally, there's writing in terms of abstract types. That's really data abstraction. But another feature that this gives you is that compile time type checking, so that you don't try and add a string and an array together. So this kind of factoring out common code is a great help to all of these issues. Reliability, basically it reduces the overall number of lines of code. And I think that the real mapping is the number of bugs you have is proportional to the number of lines of code you have. The more lines of code, the more bugs. And so if you can eliminate code by compressing redundant code into a single place, you'll have less bugs. And since the compressed code or reused code will be called more often, you'll find those bugs sooner because somebody will trigger them. Plus, when you go to change the system or extend it, you only have to change that one thing. So factoring out common code is a huge and powerful thing. Let's see, other tools we have are compile time error checking, I talked about, and just general programming style and documentation really can help a lot with maintainability and extensibility when somebody else takes over your code. I think that a well-written program, I like to think of it as not only something that's supposed to compile and run efficiently, but something that's akin to a story that somebody can read, a programmer skilled in the art, can read, and it will kind of explain to them what it's doing and how and why. And anything in its implementation that is not obvious from just reading that program as a story, you need to comment to kind of, if you do something exceptionally clever, that's when you need comments. So now to get kind of, these are again pretty high level ideas. If we think about what OOP, object-oriented programming ideas we have to support these guys, we have basically our strong typing. All right, which helps us with abstraction and error checking. It lets us compare things at compile time. Strong typing, of course, means that all of our variables have types associated with them. And those types are remembered and carried through all our operations. There are many languages which don't have strong typing and that let you put anything in any variable at any time And sometimes that's very handy, but it's not as safe. The access restriction
it's not as safe
because the compiler can't check at compile time that you're doing something bad. Basically, you have to run it and then find it something bad. And if you're just writing something for you to use as a convenience, it's not a big deal. If you shipped it to 1,000 customers, then it's going to be a problem. So access restriction, these are our favorite keywords in Java. Private, lesser used, protected. Things that limit the set of methods that can access a certain piece of data. So what this does is enforce this abstraction and this idea of encapsulating something in a black box, so you only see its behavior. You don't see its implementation. This private is kind of a way of putting a black curtain around the actual implementation. So even if somebody can look at the source and thinks they know how it's implemented, can't actually program based on how it's implemented. We have, of course, our classes. Classes inheritance, and our keyword extends is key to implementing this idea of abstraction and to factoring out code into parent classes, as well as, of course, interfaces, another mechanism for accomplishing the same thing. Our implements keyword. And finally, we have the consequence of inheritance. And perhaps the heart of object-oriented programming is this idea of polymorphism, which allows you to perform a different type of abstraction, which I guess I didn't mention, which allows you to write your algorithms in terms of abstract types and operations on abstract types. So in our problem set, we wrote operations algorithms that worked in terms of kind of a general notion of function. And then we depended on polymorphism to implement that for each particular type of function that we described. But our algorithms could be written at a very high level. We didn't have to write for a separate bracket root for sine and a separate one for cosine and a separate one for each class. We could use the same bracket root algorithm for all of the different cases. So that allows you to write your algorithms in terms of these high-level types. Building class hierarchies, just a little bit of advice on OOP design. One of the problems we gave you on the problem set was, here's a bunch of classes, arrange them in some kind of hierarchy. And there's no hard and fast rules for what you should make classes and how you should rearrange them, but there are methodologies that have evolved, and there's some general principles. And the part of the general principles is to think about the relationship in English conceptually between the two types of objects that you're wondering what the relationship is. And the main relationships we kind of talk about are is-a, has-a, uses, and I think I made up this one, or made up this terminology, but it's nonetheless relevant to something. And these pretty much have the meaning that they have in English, which is why they're useful. And ISA generally indicates inheritance. There are kind of a couple rules as to whether you should use inheritance in a given situation. First of all, is it natural? If you have two classes, say duck and bird, should you use inheritance, or is it legitimate to use inheritance? You can say, yes, a duck is a bird. So anything that you can say for class X and class Y, if X is a Y, if that makes sense in English, and it's true a reasonable amount of the time, then it makes sense to inherit from X to Y. And in inheritance diagrams, the arrow usually points to the parent class. Another key to, even if things have the ISA relationship, whether it's worth going through the trouble of putting them in a subclass, superclass relationship, sometimes depends on whether it's how you're going to use them. And the key thing to ask yourself here, am I ever going to upcast? Am I ever going to call a function on the parent class? And if the answer is yes, you definitely should use inheritance. If the answer is no, then maybe you're not. Maybe the superclass isn't buying you anything. Though if you have a lot of different subclasses and you're sequestering some common data on the superclass, then again it is. But ISA is a pretty good term for inheritance. All right. HASA is a different relationship, which is sometimes easy to get mixed up with ISA and inheritance hierarchies, because it is a hierarchical thing, but of a different nature. It's basically the relationship between a thing and its components, okay? Or a thing and its properties. So if you can use the word HASA, for example, for horses, you can say, if you think in terms of components, or automobiles. Automobiles have wheels. They have an undercarriage. They have brakes. So anything that has that component relationship, anything that you can say HASA in English, corresponds to this relationship, and this will correspond to basically instance variables. If you have something that, if you have a class X, which you can say has a Y, so X has a Y of some sort for any two things, it would be likely you would get something that would look like this. Okay, if I say X has a Y, that means the class X probably has an instance variable of type Y in it. Or if it has many Y's, you might have an array of Y's in there. For example, wheels, if you were doing a car has 4 wheels, so you would have an array of type wheels in there if you wanted to organize things in that fashion. The reason this one and this one are often confused is because they both kind of tree-like representations of the way things are, but this one is representing kind of a containment tree of parts building up to form a whole. This one is more a kind of philosophical, ontological tree of what is, of more philosophical types of higher level ideas versus more abstract or more concrete, rather, ideas. Zen and the Art of Motorcycle Maintenance, by the way, is a great book to read to kind of think about these issues. At least the first half before the guy goes crazy. All right. Our remaining relationships, the uses relationship, is that you have class X that's doing its job, and in order to do its job, it has to use some other thing. For example, our bracket root routine, you could say, uses something of type function because it has to call evaluate to do its work. And the uses routine is the uses relationship usually implies some kind of method call. So if class X or method foo uses class Y, then some method of class X will call some method of class Y, or our method foo will call some method on Y. So uses represents method calls. And the thing that's being used can either be stored, sometimes it's kept as an instance variable on the class that uses it. Sometimes it's just passed in as an argument to some method on the class that uses it. So, and finally, behaves like, which is something that's very similar to ISA in that you're trying to take a bunch of things with common behavior and think of them as a single entity. But it's somewhat weaker than ISA in that you're not necessarily want to go all the way and say that this is a something. And it's basically, it's a little bit weaker, and it's distinguished in Java because we have these interfaces. All right, behaves like is generally if something behaves like something else. For example, a fish behaves like swimming things or things that move underwater. Say, for some reason, you had a class of a notion of things that behave underwater. Now, submarines also move underwater, as do dolphins and whales. And you might not want to go so far as to say that there's some common class of things that unify submarine, fish, and dolphins into something that you can say is a, but they certainly behave like they all have this similar piece of behavior. As I say, to a certain extent, the distinction of this and this is a little bit mushy, and indeed in C++, these are implemented in the same way. Since you're allowed multiple inheritance in C++, you don't have to worry so much about these distinctions. In Java, since you only get one superclass and everything else, every other piece of common behavior you have to do with interfaces, it makes sense to keep that phrase in mind.
Can a class both inherit and interface from other classes? Can it have both at the same time?
Yes, it can inherit from one class, and it can implement any number of interfaces. So,
Is that pretty much the only reason why you would want to use interfaces rather than inheritance, is when you want to be able to do that?
to do more than one, or it's the only reason you have to use interfaces. Other than that, it probably boils down to a stylistic choice of whether you think that the interface idea, or the idea you're trying to express, is really a set of behaviors, or is in some sense a class in that it would have, for example, data items that would go along with it. If some notion in your mind naturally has pieces of data associated with it, it makes maybe more sense to do it as a superclass than as a interface, since you can't really carry around instance variables in an interface. So, yeah.
What was the case where it's necessary to use interfaces?
Oh, and necessary to use interfaces if you want to essentially inherit from more than one parent class. You can only inherit from one in Java. So everything else you have to make interfaces. And that differs from C++.
Now, the specific implementation of interface functions within a class can use the instance variables of the class. And things
Right.
like that, so-
Right.
Okay.
in general, are object-oriented languages like C++ or like Java? The other languages?
Well, those are the big two, so.
Things like small, I mean, are those things even used at all?
I would say outside of research ideas, probably not. I would say that Java is probably a subset of the C++ ideas. C++ gives you interfaces as you can make these abstract classes, purely abstract classes, like you can in Java, and just have a class in C++ where all of the methods are unimplemented, and then treat that just like an interface in Java. But C++ lets you go farther and have like fully implemented classes and then combine them into a child class. And people who have done that regret it, because to keep it straight of how these data members get inherited, and say somebody gives a data member of the same name in these two superclasses, to remember which one gets priority and which one you're actually talking about at any given time, drives people crazy. So most sane people who use multiple inheritance in C++ will do one class, will structure it this way, have one main parent, and then other parents that are basically more like interfaces in that they're mostly abstract and don't have any data members. That would be certainly the way I would do it. In the 10 years or so I've probably been doing C++, I've never used multiple inheritance. But for those of you interested in quizmanship, these would be good things to remember.
Are your quizzes?
Can I erase them now? All right, they're in the notes. I think today's notes are actually fairly complete. All right, now we're going to just try and think about the design process and walk through a design, hopefully with some interaction from the audience. And the thing we're going to try and design is the game Tetris, my little drawing. I assume you all have seen Tetris and know how to play it. No. What? Oh my God. All right, well.
Let's just go through it quickly. What happened here?
Blocks of different
All right.
shapes.
Actually, this is step one of the design process. So we can learn this in step one of the design process. So when you have a process like this that you're trying to design, okay, the last thing you want to do is to go in and start programming, like say, how am I going to draw these blocks? Maybe I'll write a little block draw routine. The first thing to do, as we said before, is to stop and think. And the design process is basically that stopping and thinking. And when you have a fairly, this is not a trivial system, nor is it a very complicated system. It's a single module. It's not something we have to worry about, 10 things from 5 vendors running on 6 machines, which is a whole different sort of level of design. But this is a single module or a single subsystem. So the first thing we want to do, step one, is just write out in English or some pseudocode what it does. Now, if you have a bigger system, this whole phase is like a whole project phase, the result of which is a specification document that has like 5 chapters or 10 chapters and is like 100 pages long. But since we're doing it, so can somebody describe to me slowly so I can write what Tetris does? What happens? Say you start up the game. What happens?
A board is drawn.
A board is drawn, right? All right, so once you have the board going, you say new game, what happens?
Piece falls.
piece falls. Okay, so let me break that up into 2 steps. Piece, let me call that. No, that's good. Piece enters, and I'm going to call that thing, I'm going to call it the well. All right, and then piece falls. And it falls slowly. All right, what else goes on in Tetris? So now we have this guy. He started up here, and he's falling slowly. Rotate, okay. So in response to user input, we rotate piece, and we shift the piece. All right, what's so funny? Did I screw up? No. Oh, okay. Okay, what else happens? Hits the bottom. It hits something. Okay. When piece hits something, it stops. All right. And what else? What happens before it starts a new block?
Checks to see if you get a line.
Right. If you have a complete row, this row will disappear. So it checks for complete row. It deletes complete rows. And what's the last thing that happens after it deletes the rows? Right, everything. So we'll call that, it compacts the well. And then score, right. It means that anything up here on top of this row that gets eliminated drops down as if under the influence of gravity till it hits something below it.
So we need to do another check for rows then after the compacting?
Yes, yes. That's right. You have to iterate that until no rows change.
You compact the pieces. Pieces don't fall. It's not like they fall one.
Hmm?
They just fall one.
The original Tetris still just fall one.
Oh, that's a good point. That's a good point. You're right. This whole chunk falls until the first thing hits something, and that's actually consistent semantically because everything else up here is supported by at least one thing. So nothing up here can fall, and therefore...
But it does fall until...
Right. It falls until this guy, that surface, hits something, which would be here. So.
But if that block wasn't there, then it would fall too, right?
Right. If this block wasn't here, then it would fall down there. And everything above it falls. All right. Well, this is cool. This is looking less difficult.
So would game over be under what piece hits something stop?
Right, right. When game over happens, that's another operation. Basically, when the well fills up so that the piece that enters can't go anywhere, you lose. So okay. Excuse me? Oh, it's inevitable. You always lose. Yeah, it's kind of like Missile Command.
In the Game Boy one, you go to you win.
Until you get a job.
Oh, really? So,
The bottom row needs a gap or it would be deleted.
oh, this is a gap.
Oh, sorry.
All right. Now the next step in our design, this is looking pretty good. The next step in our design, since we're doing an object-oriented way of doing design, is to think, what are the classes? What are the natural objects we need to implement this? So any suggestions as to what would be a good kind of type of object? Piece. Excellent. I call these blocks in my design, but score. And board, yeah. And our well. And I think that's about it. Squares, yeah. Squares would be good. They have maybe they don't do very much, but it's nonetheless better to think of them in terms of abstraction. Write the thing out abstractly. If your square class seems a bit too lame at the end, you can eliminate it. And so, oh, I know one. What?
Would squares make up your different shaped pieces?
Yeah, no, pieces would be this. Squares would be each individual little thing in the well we would label as a square. As I say, it doesn't do anything very interesting except sit there, but it has colors like property. Okay, and remember, as these things, what did I say?
Colors like property.
Oh, okay, properties like color. And remember, as this kind of elimination of rows happen, pieces lose their individual identity because you can sometimes wipe out 2/3 of a piece but still have a block or a square lying around. So it makes sense to have a separate idea that's a square and a piece. Yeah?
I have two questions on the operation of the game.
Okay.
I'm familiar. Which row has to be complete in order for there to be a movement down?
Oh, any row at all
So the way
that
you've
completes.
shown it is going to be
Right. This row would get eliminated, and this guy would, it just vanishes.
oh, it vanishes to the left. Of the
Oh, it just poof, it just goes poof. And and everybody else falls down until this guy hits something. So we're not going to go so far today as to actually implement all those little things, but we want to break the thing into small enough pieces that you can, in your mind, imagine you could implement them. Our next step is to think about what pieces of data kind of go on each one of these things. I want to mention one other one, and I will call it well display. All right. One of our first things on here is to display the board. And one way to maintain the well, okay, our well data structure is to just keep all these pixels around and do everything in terms of kind of the representation on the screen. This would be an exceptionally bad idea. And what we would like to be able to do is represent and write our well class in such a way that it's easy to express the semantics of the game, the operation of the game that we just talked about, and then worry at some other point in some other class about how to draw that on the screen, how to do all the updates. And this is what we would call in software engineering an example of a design pattern. Okay, there's a lot of problems that come up again and again in computer science and building systems, problems that have been addressed, and eventually some kind of common wisdom in folklore has been built up about what the best way or a number of ways to address these things. So essentially there's a bunch of wheels out there that have already been invented and studied, and when you are thinking about your problem and designing your problem, you should know what these wheels are and use them if you can, rather than reinventing them.
So what did you say was a really bad idea?
Oh, to think of implementing this thing in terms of its representation on the screen, a bunch of dots on the screen. So this is an example of a design pattern, very common, called, and these things have evolved into a whole industry of people writing books on design patterns and publishing tools for design patterns and having design pattern conferences And then it's spawned another movement called anti-patterns, which are common things that you do that are bad and how to fix them. But this one is called the model view controller. And it occurs very frequently in any kind of graphic or user interface type application. The idea is to have an underlying data structure, which is the thing that your program is manipulating, which is called the model. Okay? In our case, the model is this collection of classes. It's basically in some abstract representation, the state of the game with the score, the current state of the pieces, the blocks, the wells, the squares, all that. That's our model. And that's stored in some way that makes it convenient to do the operations of the game. The view, its sole job is to take the model and display it to the user. And the nice thing about breaking things up this way is that you can keep the same model, for example, and then totally rewrite just the view part, and you've got a different look and feel on your underlying model. Or it might be convenient for a single program to allow multiple views of the data. For example, if you have a document editor like Word, this has some data structure in it that represents what you've typed. You might want to have the normal view, which is kind of as if you would print it, and that's what you're editing. You might want to have another view, which just gives you a hierarchical view of the kind of chapter section heading structure. So that's the same model, but two different views that you can give the user. So that's why this is very powerful. Controller is, I think, a less commonly used feature of this, but the controller is just the abstract thing that manipulates this. So it allows you to abstract, which button or which control you bind to the operation of rotating this. Okay, you have an abstract operation, which is rotate block, and then you can bind that to the K key, to the J key, to somebody clicking their mouse on a rotate block button. You can provide multiple controllers for the same basic operation. So this is a very common design pattern, model view controller. It's a good thing. Okay, step 3. Is now that we know what our classes are, our objects are, we want to start to flesh them out and start to put down, not implement, but just write out methods that would let us implement these various things. So let's see, and think about where we want to keep what information. So, all right, I'm not going to do too much syntax here, but so piece, what kind of methods does it have? Ones that make sense maybe are, maybe it has a rotate method. Shift. Fall. Pattern?
Yeah, to show the different patterns that it has.
Oh, right. It has data, which would be its I'll call it shape. It has its shape. Let me run. I'm going to just translate these down here. Okay, so these are our methods. Here are our properties. It has a shape. It has a orientation. It has a position.
Do you mean horizontal position?
Yeah, I mean both horizontal, I guess, and vertical. So maybe we want to have that, both of those.
Are we going to have a position node in it, or how? Because they're not square objects, all of them.
Right, but say, well, this is a good question now. This gets into how do we want to represent the shape? But we need just to stay not quite that detailed. We need an x pos and a y pos, let's say, which represents.
But what does that represent? I mean,
It represents, let's say,
shaped guy, what part of it is going to be the
right, from some reference point. All right, so we'll leave it a little vague at the moment. We'll just say from some reference point.
But is this where we put the border states in under shape? That's where we're keeping X pos and Y pos?
The border states.
Well, you're going to have to do collision.
Ah, right. Now, here's a question. Okay, this brings us to where we want to do some of these other things. And we have our collision detection hit something. And where's a good place to do that? Say we put it on piece. Okay, what information do you need to do collision detection? You need to know where the walls are. What else do you need to know to do where all the blocks are? So where does that information naturally live? In the well. So my preference would be to do collision detection here, where we pass in a piece, and the well is going to tell us, this routine will tell us whether there's a collision or not.
So piece would have to have the coordinates of all four of the component pieces.
Right, piece, in order for this to work, well would have to somehow have access to or be able to get at, you're right, the coordinates. And since piece is a general thing, it would have to be somehow,
An array of pairs.
right, it would have to be, we would have to have some relative coordinate system to the piece, okay, that would tell us where all the squares in the piece were. And probably that would have to be some kind of 4x4 thing, okay? And then we know kind of the position of this corner in the well, which would be actually the position of this piece.
I don't think you can go by the corner because when you rotate the piece, it rotates around the center.
That's true. So what I would have to do here is, I mean, we need a 4x4 block.
Like the center, you
Right.
use only 4 positions.
Exactly. We use 4x4. The trouble with the 4x4 rotations is there is no center, right? These things have to be aligned on square boundaries. So if you have something like this and want to rotate it, you kind of have an arbitrary choice of rotating it around this guy or this guy, right? But again, say we had that, say here's our representation of that, and we wanted to rotate it, we could still keep it in the 4x4 block, and it would be this, right? So we could either have code when we do our orientation that switched it from here to here, or we could just pre-compile all the different orientations. Right, so this implies that the shape thing here is what its type is something like square 4, 4. Okay? All right, that's our shape. And
The shape can be one square or all 16.
actually, in Tetris, the shapes have only 4 blocks. They're all possible connected orientations of 4 blocks.
Oh, okay.
So I won't draw those all out for you, but
Hence the name.
probably, yes. So now we have a representation for our blocks. Similar representation for our well. This whole thing is just a big array of squares. So square, comma, and it would be whatever our, this is probably not valid syntax, but bear with me, width, height. We're still in the conceptual phase. So this is just an array of squares, and we can use null, the value null, to represent any empty guy. and then an actual square object, a non-null value, would represent the thing that was full. So what can we do in here? Let's see. We can have a routine check rows. That makes sense. What other methods would make sense in well? Remove. Remove row. Shift. I'll call it compact to distinguish it from the block operation. Update score. Why not? Well is a handy enough place to put score. So it has, we have the square array. This is our variable squares. We have a variable int score. We need a pointer to the current piece. So we have our piece. We'll call him P. Let's see.
Use something to get a new block going.
Right. We need start game. Right. And start block.
Drop the next block out.
Right. Just running out here. Block.
Add the piece to the well.
Right. Last one, I'm going to put it over here. This is add piece. And this is our piece P. And what this does is once it's dropped as far as it can, it kind of loses its identity as a piece and becomes just a set of blocks in the well. So what this does is take our piece P, copy its blocks into here, and then just forget about it. And we're ready to start the new piece. Okay, as soon as you start a new piece, the old piece will no longer have any references to it. So Java will take care of it. That's one of the nice things about Java. In C++ or C, you would have to worry a lot about all of that stuff. Let's see. We have our, what else do we have? We have our little square type, which just really has one thing, color. And we'll just call it type color without worrying about what color is. We could either use the kind of underlying color representations that this display uses, which is probably not so good because it removes a little bit of separation of display technology to implementation. We might like to take the core of our game and be able to port it to a whole different display environment. So we would probably end up defining some abstract color types, our own values for red, blue, green, whatever, assign them to integers. And that's pretty much all square does, is it remembers what color it is. Because its position, it's really just a placeholder for that array and this array. Okay, so this is looking pretty plausible. The stuff that we haven't talked about is how to translate from the user pressing the K key on the board to us calling the shift routine. And the shift routine probably needs a direction. We'll make that an integer direction. And so does the rotate. If we wanted, we could probably make rotate to the left, rotate to the right, shift to the left, shift to the right, and not have any arguments. Choice is yours. So we haven't talked about how to take this model and display it on the screen. We're going to talk about that on Thursday, probably. We have not talked about how to get that key press and get it so that it calls this rotator shift routine, whichever is appropriate. We haven't talked about that. But these are the basic pieces. Now certainly we need a main routine that calls all these pieces, that basically says start game, then does a while loop that does something like start block, starts to run a timer loop to drop block, and then checks every time something happens, check for collision. If we have a collision, call these various things. But thinking in terms of that, you can kind of see how you would write the top-level game loop. You now have all the different, you basically write out this thing we did in English, and you turn that into code, and each one of these things now corresponds to a method call. Now we have the problem of implementing these guys, and the next step of the design process is to look at them and see if there's anything hard that looks hard. Because at some point we're doing a very top-down design. At some point you have to do maybe a little bottom-up things, is to say, okay, this is going to look really hard. I need to focus some effort there. And if it's really, really hard, maybe I have to change the way I'm doing my high-level design to make implementing that a little easier. Or sometimes if you have something that's really hard, one of these methods that's really hard, you do an easy implementation that doesn't do all the functionality, but nonetheless lets you get the rest of the thing going, and then you go back and you fill in the functionality. I'm recommending you do that to problem set 2, that you do a not full function implementation with the right structure, and then you go in and add the remaining structure. The only thing that looks remotely hard here, I think, would be collision, because there's a lot of cases. You basically, but it's just tedium, you basically have a access through accessors or something to this 4x4 square array. And if you really wanted to be a little bit more efficient and less kind of beautifully abstracted, you would actually allow the well to get access to this whole array. If you wanted to be a little more pure, you would say, get me the square at coordinate xy, relative coordinate xy. But either way, the collision routine has to detect whether a block hits here, so you can't shift it anymore, hits here, so you can't shift it anymore. If you're doing a rotate, you have to make sure you don't, the new rotated version doesn't collide with a block from the side, okay, which would mean the rotation was illegal and you couldn't do it. And you have to check whether the thing hit a block below it. But basically, it's essentially just tedium. You essentially take this local representation, offset it by the x and y coordinates, and then just see if there's any block in here that overlaps with a block in there or would be off the screen. And so it's tedious, but it seems doable. These guys are pretty easy. You change these variables, and then through some algorithm, mutate the shape into the new shape you want. You turn this one into this one. Or as I say, you probably just precompile a whole library of those, and you just remember which one is your current state. What else? Shift is pretty easy. You just affect this x and y coordinate. Check rows, that's easy. You just iterate. You have this matrix. You just iterate over each row, and for each row you go counting and see if there's a null. And if there's no null, you have a complete row. What other guys? Remove row, that's easy. You just take that row and you write nulls in all of the places. That's pretty good. Let's see, compact is probably pretty easy. The basic operation is taking everything above it and copying it down one row. So, you do this row to here, this row to here, this row to here, this row to here, blah, blah, blah. Okay? If you store it somewhat differently as if you store these row pointers, if you store the rows as an object and then the whole well as a pile of rows. You can do it by just keeping a one-dimensional array of rows and cutting out one row and just copying down the rows instead of each individual square. Slight optimization, it might help you some ways, maybe not other ways. So, but because you're doing it abstractly, you can like fool around with whichever way you want to implement it, and it doesn't affect the rest of the game. What else? You have to kind of iterate over that dropping process at each point, saying, if I drop another bit, am I going to have a collision? And if so, don't drop it that bit. Again, we know how to detect collisions, so tedious but not conceptually hard. So I have a final thing about implementing classes. Just general advice about how to go about that. I'll erase this for step 4, or implement methods rather. So the basic idea is you want to do this incrementally so that you can test incrementally. You don't want to have to build everything together, start the game doesn't work, and then you have this big mess you have to track down. So you'd like to be able to implement the methods incrementally, starting of course with your constructors and accessors, because you have to be able to create something before you can do anything, and you need to be able to get at the methods. And then it's nice to get some kind of display print infrastructure going, so you can see what's going on in these data structures. Okay, otherwise you're just programming blind. So if you don't have the whole display system going, write some little toString or print routine that will in some way tell you the state of the thing. All right. And then, of course, right away, start building in parallel a test driver, something that will let you construct things and call all the routines on these classes to make sure they're working. And then incrementally implement and test. All right, so you write some routine and you test it. And the best way to do this is to consider kind of the tree of what calls what. So if we have routines that probably don't call anything, are low-level routines like, well, maybe they do. Probably one of our lowest level routines is something like collision. So we would call that first, and then we would call things that call that. We would implement routines or methods that don't call other methods first. Okay, get them working. Then implement the methods that call them. Okay, implement the lowest level methods that just do some work. Then implement the methods that call these, which means that if these guys work, you have a good chance of debugging this guy more simply, because you just have to work on what it's doing and then work your way up the tree. So until finally you basically have main doing the right thing. So this is a good implementation and test technology. Start from the bottom of your tree, implement and test on your way up. And by tree, I mean, in this case, the method call tree. Which things call which. Eventually, you have to get to something that calls nothing but Java system functions, which you hope work. Any questions? Does it sound plausible that you could sit down and, with nothing but nothing but time and energy would prevent you from implementing Tetris, given that you know how to do the display and keyboard crap?
What's the display like?
What's the display?
Yeah, what kind of functions do you have at your disposal?
Well, at some level, you have stuff like draw square. Okay? No, Java will give you something called draw square and draw a line. And then you have to kind of compose this out of primitives like draw square, draw a line, whatever. Okay, and you have to translate those into kind of pixel screen size from your kind of internal. And that's maybe some of what Square could do, or that's what Well Display does. And you can fool around as to whether you want to try and draw these just a blank square, or whether you want to do animations or 3D or kind of little images. It gives you lots of things. Unfortunately, it's messy. It's a lot of tedium. There's a lot of different classes that Java provides you. And it just takes a lot of groveling around in the libraries to figure out how you want to do things. There's some general principles and then a lot of detail. And when we teach it, we're not going to teach the detail. We're going to leave it to you to, grovel around. And, we'll show you how to draw a square maybe, and you can figure out how to draw an ellipse or a circle or whatever. I'm sad to say that between versions 1.2 and 1.3, Java has complicated the process of drawing a square by probably a factor of 2 or 3, and probably added that level of inefficiency also into drawing a square. On the other hand, they claim they've made it much more general and much more powerful. That is a really good question. But you would be surprised, I guess. Well, in truth, it's to accommodate the fact that you might want to draw it with different line widths, line types, different colors, different shadings, just this whole mess of stuff, which it used to be. There used to be just a routine draw square, and you'd kind of pass some of these parameters in or set them up someplace. But now you've got to do a whole mess of rigmarole, which isn't that bad. I'm kind of complaining a little, but is nonetheless, I think, a bad idea. We will see the same effect on Wednesday when we talk about input-output. Input-output is something which is relatively simple in a language like C, and to do the same thing in Java is just a nightmare. It's just, there's a lot, in order to be very ideologically pure and general, they've made it very hard to do a simple thing. You can do lots of very complicated things, which you never want to do anyway, but they've made it, in consequence, relatively hard to do a simple thing. So something that would be 1 line of code in C would probably be 20 in Java.
Is that because everything has to belong to a class?
It's not only because everything has to belong to a class, it's because they multiplied the number of classes from what would be the equivalent of 2 maybe in C to something like 60. So, factoring out every different potential feature you might want to add, gets a new class implementation. So what I/O processing is essentially is gluing together a bunch of these till you have kind of the behavior you want, and then going on with your life. But that's not till Wednesday, so.
Fast enough to do this?
I would hope so. This is not, this is not a lot of computation going on, but it might not. It might not. So the only way to do it is try it and see. Certainly you could write it, this whole design process goes for a C implementation or a C++ implementation. You would do it exactly the same way and implement it exactly the same way. And instead of writing this display driver in Java, you would write it in X Windows or something. And then it would go pretty fast.
Are there translation programs from Java to C?
I don't know. Probably not, because Java has this whole runtime stuff with garbage collection, and that's very hard to port into C without essentially reproducing Java. But conceptually, all it means by hand to translate something from Java to C is to implement some of the mechanism by hand and be careful about how you're doing your storage allocation and clean it up yourself.
So could you imagine you write some of the code in Java and other code in C?
You could do that. You could write your whole kind of display stuff in C and then kind of your higher level stuff in Java and use this Java native interface to call down. And there might be a trend towards doing that for building up things that have to be efficient. Treat Java as essentially a scripting language for C libraries, yeah. But of course, then you're competing with other scripting languages like JavaScript or Perl or whatever, which can do the same thing. They can bind down into the native C. Or Tickle. Philip's system uses, at the very highest level, Tickle to do a lot of its stuff, but it's calling down to a lot of native functions as well. So, anyway, any more questions? I hope I have shown you that you can take something that at first looks relatively complicated to build, and by going through this process, top-down, break it up into smaller and smaller pieces so you can envision how you might implement all of the pieces, and then envision how to put the pieces together, and then you're there. Tomorrow we'll go back to new technology.